The basic material for the chips is a 1 millimeter thick silicon wafer. This is a tiny cutout of a wafer edge, 1/4 of a micrometer. First, the conductive or non-conductive layers are produced by oxidation of the surface at approximately 1000 degrees Celsius in a high-temperature furnace. A drop of photoresist is uniformly distributed by centrifugal force on the oxide layer produced, thus creating a light-sensitive layer. Special exposure machines, so-called wafer steppers, transfer the masks by exposure to the silicon wafer. The accuracy of adjustment to the features already produced must remain within a tolerance of 1/100th of a micrometer. Next, the photoresist-coated wafer is exposed through a mask. The exposed section can be developed, while the unexposed feature remains. The oxide layer is etched off. This etching process is carried out either by wet etching or plasma etching. In plasma etching, special gases combine with the layer to be removed. This makes it possible to remove the microscopically thin layers inside the windows created by exposure, development, and etching. After dissolving the remaining photoresist and then cleansing, another oxidation takes place. This time, a very thin layer is affected. Electrically conductive polysilicon is deposited on this insulation layer. Then, once again, photoresist, mask, and exposure occur, and the exposed photoresist is again dissolved. Then, the polysilicon and the thin oxide layer are etched off. They both remain intact only in the middle under the resist layer. In the next step, an ion implanter shoots impurity atoms into the silicon. This changes the conductivity of the exposed silicon by fractions of a micrometer. Structure widths, distances, and cover precision are constantly checked. After the residual photoresist has been removed, another oxide layer is applied. Once again, the cycle of photoresist, exposure, removal, and dissolution takes place. Contact holes are etched in to open up access to the conductive layers because the contacts and interconnections must now be deposited. For this purpose, metal compounds are sputtered onto the wafer in sputtering machines. Once again, photoresist and mask. Depending on the component, over 200 meters of interconnections are created. The unexposed strips show the path of the aluminum conductor tracks that remain behind after the etching process and provide the contact to the underlying layers. More and more often, aluminum interconnections are being replaced by copper ones because the outstanding electrical conductivity of copper guarantees an extremely high data transfer rate. The insulation layer above the interconnections must be given a smooth surface, which is why the CMP, the chemical-mechanical process, is used. Excess material in the micrometer range is polished off. In this production line, the individual work processes are repeated 400 to 500 times until the integrated circuit of a component is completely assembled.